If you've ever felt like getting a machine learning model from, just an idea to actually working in the real world is less of a smooth journey and more of well, a trek through a dense, tangled jungle, you are absolutely not alone.
Oh, definitely. Data, training, infrastructure, deployment. It's a lot.
It really is. It's such a complex life cycle, right?
Yeah.
So many different tools, so many steps.
Yeah, and keeping track of it all, making sure everything actually works together seamlessly, and then thinking about scaling it up. That's where things can get pretty tricky fast.
And that's exactly why we're doing this deep dive today. We've been digging into, a whole stack of Google Cloud documentation pages, plus an article that really talks about the purpose and potential of Google Cloud's Vertex AI.
Right. Our mission here is to try and cut through some of that complexity. We want to unpack what Vertex AI actually is, understand why Google Cloud built it this way, and, figure out how it's supposed to help tame that whole ML lifecycle.
Extracting the core insights, the practical steps from all this material, basically giving you a shortcut to being well-informed.
Exactly.
So let's unpack this then, starting right at the top. What is Vertex AI? And I guess more importantly, why would someone choose to use it over, say, trying to build their own ML infrastructure piece by piece?
Okay, so at its core, Vertex AI is presented as a fully managed machine learning platform on Google Cloud. Think of it less as just a collection of separate services and more like a unified workbench. It's designed specifically to simplify that whole build, deploy, and manage process for ML models.
Okay.
And the big promise is that you don't have to get completely bogged down in the nuts and bolts of the underlying infrastructure or scalability or performance tuning right at the start.
So it's really about bringing everything under one roof. Is that the main idea?
That's definitely a key benefit. The sources emphasize this unified platform idea. It really aims to streamline that entire AI development lifecycle, from the moment you start prepping your data all the way through to monitoring your model once it's live in production. And this unification, it's actually really important because it helps you avoid the headaches of trying to stitch together like 10 different disparate tools.
Which can be a nightmare, yeah. Version conflicts, integration.
Exactly. Integration nightmares, wasted effort. It tries to smooth that out.
And I imagine running on Google Cloud infrastructure, that must give us some inherent advantages, especially thinking about scale.
It definitely does. Scalability and performance are really significant benefits highlighted because it's built on Google Cloud. It can leverage that infrastructure to handle growing workloads and, massive data volumes pretty efficiently.
So you get access to the powerful compute,
Yeah.
GPUs, CPUs.
Right, without having to personally provision, configure, and manage all those virtual machines yourself. It's designed to scale with your needs.
Okay, what about someone who maybe isn't a deep expert in every single ML framework or, the fine art of hyperparameter tuning? Does Vertex AI help democratize ML a bit?
Absolutely, and that's where features like the pre-built models and especially automated machine learning or AutoML become incredibly valuable.
Right, AutoML.
Yeah, these aren't just sort of nice-to-haves. They can seriously speed up development. AutoML in particular makes ML much more accessible, even if your coding expertise is, let's say, limited. It handles a lot of the heavy lifting.
What kind of heavy lifting are we talking about?
Things like parts of data prep, model selection, tuning hyperparameters, even getting the model ready for deployment. It allows you to train models for many common tasks without writing much code or sometimes any code at all.
That sounds like a huge time saver, especially for prototyping maybe, or for teams that don't have dedicated ML engineers on staff.
For sure.
So what happens once a model is trained and you're ready to actually put it to work?
Well, Vertex AI provides pretty robust model management tools. This includes things like versioning, keeping track of different iterations of your model, very important, different deployment options, and crucially, monitoring capabilities. Because, in the real world, models degrade over time, data drifts.
Right.
Performance drops. Exactly. And you need tools to track their performance and make sure they stay accurate and reliable. Just keeping track of different model versions and understanding how they're actually behaving in production is essential for maintaining the value of your ML application.
And ultimately, the goal of doing all this is, better decisions, right?
Precisely. By making it easier and faster to build, train, and deploy accurate models, Vertex AI helps organizations or even individuals really to extract those AI-powered insights from their data.
Identifying trends, anomalies.
Yeah, spotting anomalies, recognizing patterns that maybe wouldn't be obvious otherwise. It enables better data-driven decision-making.
And the article also mentioned cost. How does that factor in?
Yes, it's typical of cloud platforms, right? It operates on a pay-as-you-go model.
Hmm.
So you pay for the compute and the services you actually consume. And the platform's design, because it's managed, aims for efficient resource allocation, which can lead to cost optimizations compared to, say, managing your own hardware and software stack where you might have resources sitting idle a lot of the time.
So if you're maybe a learner, someone wanting to understand and apply ML, but maybe feeling a bit intimidated by all the underlying complexity, Vertex AI is trying to provide that structured path, that automation.
That seems to be the core pitch, yeah. It's really about lowering the barrier to entry for getting ML models into production by handling a good chunk of the operational complexity for you.
Okay, that clarifies the why pretty well.
Yeah.
Let's get into the how then. Once I have my data ready to go, what are my options for actually training a model on Vertex AI? The sources seem to highlight two main paths.
Right. You've basically got two primary routes, and it depends on your needs and your level of expertise. There's AutoML, which we touched on, and then there's custom training.
Okay, let's dive into AutoML first. This is the one for less code you mentioned.
Exactly. AutoML is designed to be the low-code or even code-free option. It automates a really large chunk of the machine learning workflow for you.
Like what parts?
Well, everything from parts of data preparation and feature engineering, right through to selecting the best model architecture for your problem, tuning the hyperparameters, and even packaging the model up for deployment. Basically, you tell it what you want to predict, you give it your data, and it goes to work.
And what kind of data can it handle? Is it just tables?
No, it supports several common data types you typically encounter in ML tabular data, of course, but also image data, text data, and even video data.
Okay.
And for each of those data types, it supports specific objectives. So for example, with tabular data, you could do classification, regression, or forecasting. With images, you might train an object detection model or an image classification model.
And once AutoML has done its thing, trained a model, how do you actually use it? How do you get predictions?
Right. So once it's trained, these AutoML models can be deployed to something called an endpoint for online predictions. Think real-time scoring. Like, classify this image now.
Exactly. Instantly classifying an image a user just uploaded. Or, alternatively, you can query the model directly from the model registry for batch predictions,
Ah, okay.
which is better suited for processing, a large data set asynchronously, like analyzing all your customer reviews overnight.
Got it. So AutoML is that accelerated, more automated path. What about the other route, custom training? What does that offer that AutoML doesn't?
Custom training basically gives you complete control. This is the path you take when you have very specific requirements. Maybe you've designed a custom model architecture, or you want to use a particular ML framework.
Like PyTorch or TensorFlow.
Exactly. PyTorch, TensorFlow, XGBoost, scikit-learn, or maybe something else entirely that might not be fully optimized or available in AutoML for your specific task. You write your own training code.
Okay.
And you configure the specific compute resources you need. You choose the machine types, the number of TPUs, accelerators, all that stuff. So you're bringing your own expertise, your own code, and essentially using Vertex AI as this powerful managed compute engine for the training part.
That's a really good way to think about it, yeah. For the training phase, at least. You define the logic, the model, the training loop, and Vertex AI provides that scalable, managed environment to run it in.
And the output is?
The output of this custom training process is your custom-trained model artifact, which you then import into the Vertex AI model registry for management, just like an AutoML model.
The documentation also talked a bit about packaging up your code for custom training. It's not just like throwing a single Python file at it, is it? Although maybe sometimes.
Well, you can actually start with just a single Python file for really quick experiments, which is quite handy sometimes.
Okay.
But for more complex projects, maybe you have multiple files, helper modules, dependencies. You typically package your code as a Python source distribution, like a standard Python package, and you store that package in cloud storage.
And the most flexible options seem to involve containers, like Docker.
Yes, custom containers give you the absolute most control. This becomes necessary if your code isn't pure Python, maybe it has complex system dependencies, or you just need a very specific controlled environment.
How does that work?
You build a standard Docker container image using a Docker file, package all your code and dependencies in there, and then you push that container image to a container registry. Google Cloud has its own called Artifact Registry, but others work too. It's just a place to store your container images.
Okay.
But regardless of how you package it, single file, source distribution, or container, There's usually a main entry point script, often named something like task.py, typically located within a trainer subdirectory in your code structure. That's what Vertex AI runs.
Right. Okay, so let's say we've successfully trained a model,
Right.
either quickly with AutoML or with that fine-grained control using custom training. Now we actually need to use it, get predictions. The source is mentioned. The model registry is the next stop.
Exactly right. The model registry is like the central library, the catalog for all your trained models within Vertex AI. This is where you register your models, whether they came from AutoML or custom training.
And you manage different versions there.
Yes, you manage different versions. You can add descriptions, labels, and importantly, it integrates tightly with the features for model evaluation and deployment. It really becomes your single source of truth for all your trained model artifacts.
Okay, so the model's in the registry. How do we actually get predictions from it? You mentioned 2 ways earlier. Is there just one method?
No, there are two distinct ways to get predictions, and it's actually a really important distinction to understand based on your needs. You can get online predictions or batch predictions.
Okay, lay out the difference for us there. Online versus batch.
Sure, online predictions are designed for those real-time, low-latency requests. Think about scoring a single data point, like right now.
The fraud detection example.
Exactly, like predicting if a credit card transaction is fraudulent the very instant it happens. Now, to do this, your model absolutely must be deployed to what's called an endpoint.
Okay, so online needs an endpoint. What about batch predictions then?
Batch predictions are for asynchronous processing of large volumes of data. So this is more like taking a whole database table of customer data and scoring every single row all at once, maybe overnight, to identify different segments or predict churn.
Right.
And the key difference here is that batch predictions do not require deploying your model to an endpoint. You essentially just point Vertex AI to your registered model and your input data, usually in cloud storage, and it handles the processing as a large offline batch job.
That's a fundamental difference in architecture and probably cost too, I imagine.
Absolutely.
So if you need that instant real-time response, deployment to an endpoint is the way to go. What does that deployment step actually do under the hood?
Right, so deploying to an endpoint is the crucial step that associates physical compute resources, those virtual machines with CPUs or GPUs, with your model artifact from the registry.
It makes it live, basically.
Exactly. This makes the model accessible via a live service endpoint, which is essentially a URL, ready to receive those low latency online prediction requests from your application.
And I assume I have to make some decisions about those machines, the resources, when I deploy.
Yes, you do. You configure the compute resources during the deployment process. You choose the machine type, how powerful it needs to be, whether you need GPUs, how many. And you also specify the minimum and maximum number of replica nodes you want for scaling, which we can talk more about. But the sources make a key point here. Some of these crucial settings, specifically the machine type you select or the container image you use if it's a custom model,
Yeah.
those cannot be changed after the model is deployed to that endpoint. If you realize you need a more powerful machine type later, you actually have to undeploy the model and then redeploy it with the new configuration.
Ah, okay. Immutable settings after deployment. That is a really good detail to know up front. So that endpoint itself, that's the network address, the URL you send prediction requests to.
Correct.
Now, why might you put multiple different models onto a single endpoint? That seems a bit counterintuitive at first glance.
Yeah, it does, but it's actually a very common strategy for doing careful model updates and testing. For example, let's say you have a new version of your fraud detection model, version 2.
Yep.
You can deploy V2 alongside the currently running V1 on the same endpoint. Then you can use a feature called traffic splitting.
Ah, like A/V testing?
Sort of, yeah.
Ah,
You can configure it to send, say, only 5% of the incoming prediction requests to the new V2 model, while the other 95% still go to the stable V1. This lets you test the new model in production with real, live traffic, but minimal risk.
and then you gradually increase the traffic to the new one if it looks good.
Exactly. You monitor its performance, and if everything checks out, you gradually shift more and more traffic over time until V2 is handling 100%. It's essential for safe, rolling deployments and minimizing risk during model updates.
Okay, that makes perfect sense for managing different versions on one endpoint. How about the other way around? Why would you deploy one model to multiple different endpoints?
You typically do this to serve different purposes or environments with potentially different requirements. A common pattern is having separate endpoints for, say, development, testing, staging, and production environments.
Right, isolating environment.
Yeah. Or another reason is performance and cost. You might deploy the exact same model artifact to one endpoint that's configured with really powerful machines and a higher minimum number of nodes to meet strict performance targets or service level objectives, SLOs, for a critical high traffic application. But then you might deploy that very same model artifact to a different endpoint, configured with fewer, less powerful resources for a less latency-sensitive internal tool or an application that's used less frequently, purely to manage costs more effectively.
Ah, I see. So using different endpoints lets you tailor the performance and cost profile for the same underlying model based on the specific application's needs. That's quite clever.
It gives you flexibility.
And how does the scaling work for these online prediction endpoints? You mentioned minimum and maximum nodes.
Right, so they can automatically scale up and down. You configure this when you deploy the model by setting a min replica count, the minimum number of nodes that should always be running, and a max replica count, the upper limit.
And Vertex AI just handles it.
Yes, Vertex AI will automatically adjust the number of active compute nodes serving your model, somewhere between that minimum and maximum value you set, based on the incoming traffic load and the resource utilization of the existing nodes.
What actually drives that auto-scaling decision? What's it looking at?
By default, it usually scales based on the average CPU utilization across your deployed nodes. There's often a target utilization level, maybe around 60% or so.
Okay.
So if the average CPU usage goes way above that target, it starts adding more nodes up to your defined maximum. If the utilization drops significantly below the target for a period, it starts removing nodes, but never going below your set minimum. You can sometimes configure it to scale based on GPU usage too, if you're using GPUs.
Now, you mentioned scaling takes time. What are the implications of that?
Yeah, that's a really important operational insight from the documentation. Scaling isn't instantaneous. When traffic spikes and it needs to add a new node, there's a delay. It takes time for the new virtual machine to spin up,
Right.
for the container image, if you're using one, to download onto that VM, and then for your actual model file to be loaded into memory on that new node so it can start serving predictions.
So if you get a sudden burst of traffic,
Exactly. If you anticipate sudden traffic bursts, the recommendation is often to set your min replicas high enough to handle your expected baseline peak traffic. This ensures you have enough capacity ready immediately, avoiding those initial latency hits or errors while the system catches up and scales out.
and that minimum has to be at least one, right? It can't scale down to 0 for online endpoints.
Correct. An endpoint serving online predictions needs at least one node running to be available, so min replica count must be 1 or greater. It can't scale down to 0 and shut off completely when it's idle, unlike some other serverless services.
Can you adjust those scaling knobs, the min-max counts, after the model is already live and serving traffic? Or do you need to redeploy for that too?
Good question. Yes, some of those scaling configurations can actually be updated after deployment without needing a full redeployment. The sources mention a specific function or API call, something like mutated deployed model,
Okay.
which lets you change things like the min replica count, the max replica count, and even the specific auto-scaling metrics or targets you're using, like changing the target CPU utilization.
But not the machine type.
Correct. That machine type we talked about earlier, still immutable after initial deployment. Changing that requires a full undeploy and redeploy cycle.
Got it. And of course, using cloud resources means thinking about quotas, I assume. How does that work with these scaled endpoints?
Absolutely. Quota usage for online prediction is typically calculated based on the real-time usage of the compute resources, basically. How many CPU hours or GPU hours your active nodes are consuming.
Okay.
It's also worth noting, though, that the sum of the maximum replica counts, max replica count, you configure across all your different model deployments within a specific Google Cloud project can potentially impact your overall project-level quotas for those resource types. So you need to keep an eye on that total potential usage when planning your deployments, not just the minimums or current usage.
Right. Planning for the worst case scenario quota-wise. Okay, so we've covered the training options, managing models in the registry, getting predictions either online through deployed endpoints or in batches. But, in the real world, an ML project is rarely just one single training run followed by one deployment, right?
Oh, absolutely not.
There are data pipelines feeding into it, maybe multiple training runs with different parameters, evaluation steps, perhaps retraining cycles. How do you orchestrate all of that complexity on Vertex AI?
That's exactly where Vertex AI pipelines come into the picture. They are specifically designed to help you automate and scale those potentially complex multi-step end-to-end ML workflows. They help turn that tangled jungle we mentioned earlier into a more structured, repeatable pipeline.
And these are built on some standard open source tech, aren't they? I think I saw Kubeflow mentioned.
Yes, that's right. They're based on the Kubeflow Pipelines SDK. The documentation specifically mentions targeting V2 and later versions of that SDK. So you're building on a pretty widely used and understood framework in the MLOps community.
Okay, so how do you actually define one of these complex workflows using that kubectl Pipelines SDK? Is it graphical?
Not primarily graphical, no. You actually define your entire workflow as a standard Python function. You use the SDK's special domain-specific language, often just called kfp.dsl within that Python code.
DSL. Okay.
And within that main Python function defining your pipeline, your entire workflow is broken down into individual steps. These steps are called components. Think of a component as just a self-contained piece of code that performs one single task in your overall workflow.
Like loading data.
Exactly. Loading data, pre-processing features, training a model, evaluating that model, maybe checking some condition, deploying the model if it passes evaluation. Each of those could be a separate component. And Google Cloud even provides a library of pre-built components for many common tasks, which can save you a lot of time.
So the overall structure, the flow, comes from how you connect these components together.
Precisely. You build your pipeline by defining how the output artifact of one component, say the path to the preprocessed data, becomes the input parameter for the next component, like the training component.
Ah, connecting outputs to input.
Right. This creates a dependency graph, technically a directed acyclic graph, or DAG, which essentially defines the flowchart, the sequence and dependencies of all the steps in your ML process.
Okay, so what's the typical workflow look like for actually building and then running one of these pipelines?
It generally follows these steps. First, you design your ML workflow conceptually, breaking it down into logical components. Second, if any step needs custom logic that isn't covered by a pre-built component, you build your own custom component. You can package that custom logic either as a simple Python function or, for more complex needs, as a container image.
Like we discussed for custom training.
Exactly the same idea. Third, you write the main Python function that defines the overall pipeline structure using the kfp.dsl, specifying which components to run and how their inputs and outputs connect. Fourth, you use the SDK to compile that Python function definition into a static configuration file, usually in YAML format. This YAML file is the machine-readable definition of your pipeline's structure and components.
And finally,
You submit that compiled YAML file to the Vertex AI pipeline service to actually execute the pipeline run. You can typically do this using the Vertex AI Python client library from your code, or often through the Google Cloud Web Console interface as well.
now these pipelines are running on Google Cloud, right? And they're
Mhm.
probably accessing resources like data and cloud storage or maybe BigQuery tables. Authentication must be pretty crucial. How does that work securely?
Yes, authentication is critical. By default, Vertex AI pipelines run using a Google Cloud Service account to authenticate to other Google Cloud services. Now, a really critical best practice that the documentation strongly emphasizes is to not just rely on the default compute engine service account that might exist in your project. That default account often has very broad permissions, sometimes even full project editor access, which is a big security risk.
So what's the recommendation?
The strong recommendation is to create a dedicated new service account specifically for each pipeline, or maybe for a group of related pipelines. Then you grant that specific service account only the minimum, most granular IAM permissions it absolutely needs to access the specific Google Cloud resources required by its components, like maybe just permission to read from one specific cloud storage bucket and write to a specific BigQuery table and nothing else. This principle of least privilege significantly reduces the potential blast radius if something goes wrong.
That makes a lot of sense from a security perspective.
Yeah.
And like any software system, I guess these pipelines need ongoing maintenance.
Yes, definitely. They're not just fire and forget. You need to keep the Kubeflow Pipelines SDK version that your pipeline definition relies on updated. You also need to keep any base container images used by your custom components updated.
Why is that important?
Well, partly for getting the latest features and bug fixes from the SDK or base images, but crucially, it's for security patches. If vulnerabilities are discovered in the SDK version you compiled with, or in one of the base container images your component uses,
Yeah.
the recommended process is to update to a patched version of the SDK, or rebuild your component with a patched base image, recompile your pipeline definition into a new YAML file, and then re-upload that updated pipeline version to Vertex AI to replace the vulnerable one. It's an ongoing process.
Okay. Can you test any of this pipeline code locally on your machine before you push it up to the cloud and run it for real?
You can test parts of it locally, yes. You can certainly test the logic within your individual custom components, maybe using mock data, and you can test the Python code that defines the pipeline structure using the kfp.dsl to make sure it compiles correctly into YAML.
But there are limits.
Yes, there are definitely limitations to local testing. Specifically, if your pipeline components are designed to interact directly with Google Cloud services that require authentication, which many components will, like reading from cloud storage, querying BigQuery, calling other Vertex AI
All
APIs,
right.
you generally cannot fully execute and test that specific cloud interaction easily from your local machine without potentially complex credential setups or extensive mocking, because the authentication relies on the service account environment that exists when the pipeline runs on Vertex AI. So local testing is useful for component logic and structure, but full end-to-end testing usually needs to happen on the platform itself.
Okay, this sounds incredibly powerful for automating those really complex multi-stage ML processes. But let's try and anchor this back to the real world for a minute. How are actual businesses leveraging a platform like Vertex AI across different industries? The article you shared had some pretty compelling examples,
It
right?
really did. It showed just how versatile a platform like this aims to be. Take healthcare, for instance. The sources mentioned Vertex AI being used for things like early disease detection,
How so?
like analyzing medical images, think retinal eye scans to automatically identify subtle signs of conditions like diabetic retinopathy, potentially much earlier than might be possible with just human review alone.
Wow, that's a really high-impact use case.
Yeah.
What else were they doing in healthcare?
Things like trying to personalize treatment plans, so
Hmm.
predicting how a specific patient might respond to different medications or therapies based on their data. Also, automating more routine administrative tasks to free up doctors and nurses, maybe things like intelligent appointment scheduling systems, or using NLP to help process patient records more efficiently. And even accelerating pharmaceutical research and development, perhaps by using ML to predict potential drug candidates or to understand complex disease mechanisms faster from experimental data.
Right. Moving over to the finance sector, they obviously deal with enormous data sets and high stakes. What's happening there with Vertex AI?
Well, fraud detection is a classic, massive use case, analyzing vast numbers of credit card transactions in near real time to spot those anomalous patterns that indicate potential fraud and block it before it happens.
Makes sense.
Risk assessment is another huge area, things like evaluating loan applications more accurately, predicting credit default risk for individuals or businesses, and helping banks manage their overall portfolio risks.
And for the markets themselves or for customers?
Yeah, things like portfolio optimization, using ML to suggest asset allocations that better align with an investor's risk tolerance and return goals. Customer segmentation is big in finance too, for offering more targeted banking products or financial advice. And even market forecasting, trying to predict future trends in stock prices, bond yields, or other financial instruments, though that's obviously a very challenging area.
Indeed. Okay, let's look at manufacturing next. How is ML maybe using a platform like this, making a difference on the factory floor and maybe in the supply chain?
Predictive maintenance is a really big one in manufacturing. Using sensor data streaming from machinery on the factory floor to predict when a specific piece of equipment is likely to fail before it actually breaks down catastrophically.
Ah, so you can schedule maintenance proactively?
Exactly. It allows for planned maintenance during scheduled downtime, preventing those really costly unplanned production stoppages. Quality control is another major application using computer vision, for example, to automatically inspect products coming off the assembly line for tiny defects much faster and maybe more consistently than human inspectors.
And what about broader supply chain or resource aspects?
Yeah, things like resource optimization, maybe finding the most efficient mix of raw materials to use in a process, or optimizing energy consumption in the plant. Logistics optimization is relevant too, finding the best routes and schedules for shipping raw materials in or finished goods out. And even things like recommendation systems, perhaps for B2B customers ordering complex industrial parts online.
Okay, and retail is maybe one of the most visible areas where many consumers interact with AI daily. What were the Vertex AI use cases mentioned there?
Demand forecasting is absolutely fundamental in retail, predicting what products customers are likely to buy, when they'll buy them, and where, which store or online, which is absolutely critical for managing inventory effectively and keeping the supply chain efficient.
And the recommendations we all see online.
Personalized recommendations, exactly. Tailoring product suggestions based on your past browsing behavior, purchase history, maybe even demographics. That's a huge driver of online sales.
Pricing and inventory seem like they'd be tightly linked too.
They are. Price optimization is another big one, dynamically adjusting prices based on factors like competitor pricing, demand signals, seasonality, current inventory levels, and just more sophisticated inventory management in general, predicting potential stockouts before they happen, automating reorders to keep shelves stocked efficiently.
What about the physical store experience? Is AI playing a role there too?
Yes, increasingly so. Things like visual search, where maybe you could allow a customer to snap a photo of an item they saw somewhere, and the retailer's app can find that product or similar ones online, or tell them which nearby store has it in stock.
Cool.
Store layout optimization is another, analyzing anonymized customer traffic patterns within a physical store to figure out the most effective way to arrange products or place promotions. Customer segmentation, again, for loyalty programs or targeted offers, and using chatbots powered by natural language processing for handling customer support queries online or even sometimes through voice assistants.
Wow. Okay, it's really clear from those examples that Vertex AI is positioned as a pretty flexible platform designed to support a really wide array of problems and solutions across, well, pretty much any industry that uses data, it seems.
Yeah, that breadth of application across different domains is certainly highlighted in the materials as a major advantage of having this kind of unified platform that's designed to cover the full ML lifecycle.
So, okay, let's try and bring this all together now. We've taken quite a journey today, haven't we? We navigated from understanding the sort of fundamental benefits of Vertex AI as a managed platform,
Right, the why.
then exploring those two main paths for actually training models, the speed and automation of AutoML versus the deep control of custom training. We talked about how you need to package up your code for custom work,
Yeah, the containers and distributions.
then how you manage those trained models in that central model registry. We clarified that really crucial difference between online and batch predictions and how you deploy models to endpoints for that real-time use case.
And the scaling of those endpoints.
Exactly, the complexities and considerations around scaling those endpoints automatically. And then finally, how Vertex AI pipelines help you orchestrate all those multi-step ML workflows into something repeatable and scalable.
And it's worth remembering, as you mentioned earlier, we've really just focused on the core workflow pieces today. The source materials also point to a whole ecosystem of other integrated capabilities within Vertex AI that are designed to support that lifecycle even further.
Like what else?
Well, things like model monitoring to automatically track performance drift and data skew once your model is in production. Model evaluation tools to help you rigorously assess how well your model is actually performing against different metrics or data slices. Explainable AI features to try and help you understand why your model made a specific prediction, which is increasingly important for trust and debugging.
Right.
There's also a feature store for managing, sharing, and serving curated features consistently across different models and teams. Tools for tracking experiment metadata when you're comparing different model versions or training runs, and even a service called Vizier specifically for doing sophisticated, automated hyperparameter tuning to find the best settings for your models.
Wow. Okay. So it really sounds like once you're sort of inside the platform, there are dedicated tools aiming to cover pretty much every aspect of the MLOps lifecycle.
Yeah.
For someone listening to this and thinking, okay, this sounds interesting, I want to maybe explore this. What were the initial practical steps mentioned in the documentation for just getting started?
Yeah, the typical starting point involves first setting up a Google Cloud project if you don't have one, and then configuring your local development environment. A key step is installing the Vertex AI SDK for Python, which is how you interact with the platform programmatically.
And app authentication.
And crucially, yes, setting up your authentication correctly, which, as we discussed, strongly recommends creating and using a dedicated service account with those very specific granular permissions rather than just relying on broad default roles. And then the documentation usually provides a set of guided tutorials. Often there are ones for trying out AutoML with some sample data, running your first custom training job, and maybe building and running a simple pipeline. Those hands-on tutorials are generally excellent starting points to get a feel for the platform.
It definitely gives the impression of a platform that's really built to try and offload a lot of that underlying infrastructure management and operational heavy lifting, allowing you, the user, to focus more on the data, the model itself, and the actual business problem you're trying to solve.
That efficiency gain, that focus shift, seems to be the central promise of adopting a managed platform approach like Vertex AI based on everything we've read.
So as we wrap up this deep dive, here's maybe a final thought for you, the listener, to consider. Given the significant complexities we talk about right at the start, just taking an ML model from a concept to a reliable production-ready service, and given how a managed platform like Vertex AI explicitly aims to streamline that entire process, how could you maybe leverage this kind of integrated environment to move beyond just training individual one-off models?
Mm.
How could you start thinking about building more repeatable, scalable ML solutions that actually integrate into real-world applications, much like those diverse industry examples we just explored? Maybe think about it this way. What single tangible ML task in your own domain, perhaps one that feels a bit manual or overly complex or brittle today, could you realistically envision automating or significantly improving by adopting this kind of platform-centric approach?
Yeah, that's a good question to ponder as you consider your next ML project or how to improve existing ones.
Indeed. Well, that brings us to the end of this deep dive into Google Cloud's Vertex AI. Hopefully this conversation has given you a much clearer picture of what it is, why Google Cloud built it this way, and how it might potentially help you navigate the fascinating but often quite complex world of building and deploying machine learning models.